Hello class, good day to everyone. I hope you have already watched the last video on Fleming's left-hand rule on YouTube. And today's lesson is really meant to help cover on some of its applications and how we can really use Fleming's left-hand rule to determine direction of current, direction of force, and direction of the magnetic field. Okay, so you will need worksheet 21.2 here, and we're going to cover all these applications right now. Now, in order for us to understand how is Fleming's left-hand rule relevant to this whole lesson itself, we must first understand what is meant by this thing called a motor effect. So motor effect, right, really refers to this effect when a current carrying conductor is placed within a magnetic field. Okay, and to explain what really causes this effect, now we all know by now that all current carrying conductors will generate a magnetic field around the conductor itself. When this magnetic field of the current carrying conductor interacts with the magnetic field of another permanent magnet, for example, then this interaction actually gives rise to an induced magnetic force acting on the conductor and causing the motor effect. We will now take a look visually how this actually happens. Okay, so what we have here, for example, is that we have a magnetic field due to the current in a wire, right? And we have magnetic field between two magnetic poles. So what you see on the extreme right hand side is the combined magnetic field of the wire and the magnetic poles. Okay, but how does this magnetic field, this combined magnetic field here actually happen? Now, I want you to imagine again, remember this is combining the wire magnetic field as well as the permanent magnetic field. So if I were to put this, I'm going to draw just very briefly over here. Okay. If I were to put this wire within a magnetic field, you notice that on the left hand side, you have magnetic field lines going up, and on the right hand side, we have magnetic field lines going up from the magnet but down on the right side of the current carrying conductor. So what happens is that this side, there's a tendency to cancel the magnetic field lines out. So the magnetic field from the current carrying conductor will cancel out the magnetic field of the permanent magnet. Of course, it is not entirely cancelled out, but what happens is that we will end up with a weaker magnetic field on the right hand side. And since on the other side we have more concentrated field lines, we come up with a stronger magnetic field on the left hand side. So please feel free to go through that part again to replay the video if you really need to understand that. But after looking at this interaction, what we can see is that point A, so the left hand side, ends up with a stronger magnetic field because the magnetic field lines are more concentrated. Whereas at the right hand side, point B, there is a weaker magnetic field because the magnetic field lines are now less concentrated. Hence, right, you can think of it like this stronger magnetic field pushing towards the weaker magnetic field, a bit like a catapult effect, okay? And hence, this electromagnetic force is acting towards the right side, and it will push this particular wire towards the right. So now we'll take a look at how Fleming's left-hand rule can be used to determine all the direction that we need for our questions in the exam. So first things first is we need to label our thumb and fingers. And for our thumb itself, right, this is the direction of the induced force. And for the index finger, this is the direction of the magnetic field. And finally, for the middle finger, it actually indicates the direction of the current. So one way to help you remember this is that our thumb is the father, index finger is mother, and the middle finger is our child. Okay, so father, mother, child, force, magnetic field, current. Okay, now one thing I want to highlight is that we don't use Fleming's left-hand rule. This is very important. Okay, to explain how an electromagnetic force arises. Okay, sometimes a question may ask you why is there an induced magnetic force, and sometimes candidates actually answer, oh, because of Fleming's left-hand rule, and this is absolutely wrong. It's nothing to do with Fleming's left-hand rule. Okay, Fleming's left hand rule is really just this rule to help you determine the direction of the induced electromagnetic force. Okay, so if you really want to explain, right, how an electromagnetic force is being induced, you need to always, and I always say this, it is important you mention about the interaction of the magnetic fields between the wire as well as the permanent magnet. Okay, so this one just a little bit of extra, but it's good to know. Actually, right, the induced force can be calculated using F equals to B I L sine theta. Okay, where B is the strength of the magnetic field, I is the value of the current, L is the length of the conductor, and sine theta is actually, this theta is the angle between the magnetic field as well as the current. Okay, so of course, if the angle is at 90 degrees, I hope you know that sine 90 equals to 1. When the angle is at 90 degrees, then the induced force is at the maximum. So what we can actually see here is that the induced electromagnetic force is at the maximum, okay, when the direction of the M field vector is perpendicular to the current vector. Okay, however, right, if the current and the magnetic field are in the same direction, then what we have is that the induced electromagnetic force is zero when the M field vector is parallel to the current vector. And if you think about it, if they are in the same direction, this means that now theta must equal to 0. And if theta equals 0, then sine theta is also 0, and hence the force must be 0. So I hope the math also helps you to appreciate a little bit how these two statements actually work here. So we're going to take a look at the previous diagram once more, okay? And this time round, instead of trying to use a stronger field and weaker field to explain, we're going to use Fleming's left-hand rule, yeah? Okay, so as you can see, right, our magnetic field is moving from north to south. So what I'm going to draw is I'll draw an upwards arrow and indicate as the magnetic field. We know that the current is moving away from us, so we indicate that with a X. Okay, so that means you know that your magnetic field index finger must be pointing up. Our middle finger points away from us, and hence the thumb, as you can see, will be pointing towards the right. Okay, so this is how we use Fleming's left-hand rule, and sometimes we don't have the liberty of actually sketching magnetic fields itself. So that's why it is useful to use Fleming's left-hand rule in order for us to find the direction of the induced electromagnetic force. Okay, now let us spend some time to do some practice on using Fleming's left-hand rule. For part A, you can see is to determine the direction of the induced force. And for part B, the force is actually given, all right? And we need to find the direction of the current itself. Okay, so let's look at part A. Now, for all such questions, what you always should do is to determine the direction of the magnetic field first, okay? And usually, you also want to have an angle that you're viewing in. So I'm putting my eye there, okay? So remember, magnetic field lines are from north to south. And if my eye is at the bottom like so, so what I'm going to see, I'm going to sketch a 2D diagram here now. So I'm going to have the magnetic field lines coming towards my eye. So that means my index finger should be pointing towards me. Okay, then you can see the current is upwards. Okay, so now your middle finger should be pointing up. Your index finger should be pointing towards you, and that can only leave your thumb pointing towards the right. So for part A, the induced force must be towards the right. Okay, now let's look at part B. For part B, same thing. I'm going to draw the magnetic field lines. It is to the left. My eye is like so again. So I'm going to draw this right now. Magnetic field line to the left. Okay, we will have the induced force. So now the induced force is actually going away from us. Okay, so that means, right, my index finger point to the left, my thumb must point away from us, and you can see that leaves you with the middle finger only pointing downwards. Okay, so that means our current must be going down in this aspect. Okay, so that is how we can use Fleming's left hand rule to determine the direction of either of the components required in these questions. For question 6, we're actually presented with two slightly different examples, but you have seen something like this before. Okay, so in part A, we are saying that a charged particle, a negatively charged particle, enters a parallel magnetic field. And what we first need to remember is that the dots represent the magnetic field coming out of the paper, whereas for part B, since it's a cross, it is actually into the paper. Okay, so for part A, you will also notice that we are looking at a negatively charged particle, and since negatively charged particles always move in the opposite direction of conventional current, that tells us that this conventional current is actually towards the left. Okay, so if I were to draw the whole idea and use Fleming's left hand rule, we have our magnetic field which is coming out of the paper. We have the current which is towards the left. So if your index finger is pointing towards, if your index finger is pointing towards you, and then you have your current pointing the middle finger towards the left, you would see that the induced force must be upwards, and hence this particle will actually follow a parabolic path upwards as shown in the diagram here. Okay, for part B is a lot more straightforward. So our current is just directly to the left again, since we take it that a positively charged particle just flows in the same direction of the current. Our magnetic field is into the paper, so let's sketch all this as shown. Okay, so since our index finger will point away from us, the current is pointing towards the left, hence that leaves us with the induced force being pointed down, and this particle will move in a downward direction as shown. Okay, so I hope that this gives you a little bit more clarity on how to answer these particular questions. Okay, so now we have an example where we have a complete circuit and we have this hanging wire that passes through the path of a magnetic field. So let's take a look at how this works. Okay, so first it says state the direction in which wire BC would move towards. So as always, right, please remember that you need to have some kind of view, and usually we were trying to view the thing from the front. You can see the current is from B to C, so that means already our middle finger must be pointing away from us. Okay, you know that the magnetic field is from north to south, so magnetic field must be upwards, so that means your index finger is pointing up, middle finger away, and you can see that your thumb must be pointing towards the right, and that means that this direction of the wire would swing towards the right. Okay, so if you explain again, I remember we talked about explanation of how forces are being induced on the wire. First, we must say that when there's a current flowing through BC, a magnetic field is induced around the wire itself. Okay, and this magnetic field will interact with the magnetic field of the permanent magnet. Okay, and hence, due to this interaction, an electromagnetic force is induced and acts on BC. Okay, so I want you to think about part C. How can we use a method to increase the angle of deflection about AD? Okay, so we're just saying another way of how do we have a greater force such that BC will tend to swing more widely. Okay, and that is where you think about all your lessons on electromagnetism previously. There are many ways you can do it. Either you can increase the current, you can strengthen the magnetic field, and etc. So hence in this case, what we can do is to add more cells in series in the circuit, and that would actually increase the current coming from the circuit before it goes through BC. Okay, Okay, so with that, we have actually completed all of our class examples, and your assignment for this weekend would be to complete pages 3 to 6. Okay, but I actually want you to turn to page 6 first because we're going to look at the question 12. Yes, that's actually question 12. There's a typo. And this is the question we're looking at first because it's a little bit trickier than the rest. So let's take a quick look. Okay, so you can see from part A of this question, it just asks you to explain how a force is being induced on the current carrying coil. So I will invite you to just see the previous example on the answering format. Just remember to talk about the interaction of magnetic fields from the wire as well as the magnet, and you should have no problems in answering such questions. What I'm actually more interested in is in part B, C, and D because I want to set the expectation of how you can answer such questions as well, especially when you talk about stating direction. Yeah. Okay, so if you look at side AB first, for side AB, we can see that we know the magnetic field is towards the right. The current, as you can see, right, since it flows from X to Y, the current must be upwards, and is this side CD is actually downwards. So what we can actually see, we can sketch the current upwards first. So our middle finger must be pointing up. The magnetic field is pointing towards the right, and that actually leaves us with the induced force that must be away from us, and hence this is actually going into the paper. If you look at side CD, for side CD, same thing, our current is pointing towards downwards. We have our magnetic field pointing towards the right. So if your middle finger is pointing down and your magnetic field, the index finger, is pointing towards the right, that leaves us with the thumb pointing towards you, and hence we will have the induced force that is coming out of the paper. So we're going to write this accordingly. For side AB is into the paper, for side CD is out of the paper. How about BC and DA? Does it move in that sense, in that based on the interaction of magnetic fields? So you need to recall that because the current in BC and AD is actually parallel to the magnetic field. So in that sense, it doesn't actually get affected, and the induced force on it will be zero since their current and magnetic field is parallel to each other, and hence I just need you to explain that there is no effect of movement on side BC and DA. For part C, so it asks you to describe the overall movement of the coil. Okay, so imagine if you are viewing from X, right? What's going to happen is that since AB moves in, CD moves out, then if you're viewing from point X, it will actually move anti-clockwise. Okay, I hope you can visualize that. And remember, we are actually looking at the vantage point of X. So you got to be very careful and explain to the examiner where you are actually viewing from. For part D, it says state a method to increase the speed of this movement. Now, since I cannot use a stronger magnet, I cannot increase the value of the current either. One thing you can recall from electromagnetism is that you can actually insert a soft iron core within the coil, and this will increase the movement because that soft iron core will actually concentrate the magnetic field lines. Now we didn't actually change to use a stronger magnet, but we actually use an iron core to concentrate the magnetic field line, so this counts as an answer as well. Okay, so we have come to the end of this video lesson, and what I need you to do over the weekend, you will actually need to complete pages 3 to 6 of worksheet 21.2, but this time around we'll do it slightly differently because I will not be actually going through the worksheet in the next lesson. I will just mark whatever you submitted so that I can hopefully see that you have understanding of Fleming's left-hand rule. Same thing applies. Please put all images into one PDF document and submit it to the Google Classroom by next Wednesday latest. Okay, please don't wait till the end of the week. I really need to be able to mark it as soon as I can. And yeah, before our next lesson, please do read up on DC motor. what it does and how it works. Okay, so I wish you guys a very pleasant weekend and stay safe. Take care. Bye bye.